So now finally we're going to see how to get these things actually working. We're going to look at the basic types of variables and objects that we're going to use in TensorFlow, and I'm going to give you some simple examples of implementation. So this first set of examples today is to show you how this can be implemented at the lowest level of TensorFlow. So we're going to use the very basic operators and objects in TensorFlow. We're going to implement a simple logistic regression, then solve the OR problem with one neuron, and then you're going to solve the exclusive OR problem building a small multi-layer perceptron. This will be the exercise part, but I recommend you following the whole lecture as a tutorial afterward during the tutorial part, and then finally trying to build the multi-layer perceptron. So this will be a bit exceptional because when we start working with more complex networks, we're going to use Keras, and so we're going to work at a higher level. But it's important for you to understand how things work in detail in TensorFlow. So let's start with the basic idea. In TensorFlow, we define a computation graph where each node is an operation, each arc is a tensor, and the operations are applied to tensors that then the result of each operation will feed the tensor into the next operation. And this computation graph, when we join together these different algebraic operations, TensorFlow automatically keeps track of the corresponding derivatives because it knows how to compute the derivatives of all these elementary functions. And so when we want to train, when we want to do backpropagation, TensorFlow knows how to propagate the error, update the weights, and so forth. So if you look at the documentation on previous versions of TensorFlow, the idea was originally that we created a computation graph and then we executed the graph. So there were two stages, creating the graph and execute it, and this helped TensorFlow optimize the execution. For example, distributing different parts of the computation through the CPU, the GPU, different processors, and so on. We can still do that, and if you want really to optimize your execution, this is a good way of doing that, creating the graph and then executing it. But the default now is eager execution, which means that when you run your script, at each step when the interpreter is reading the different instructions, the TensorFlow is already computing everything step by step. So this is a bit more intuitive and easier to use in programming. It may not be as optimized for execution, but in our case, we're going to use eager execution most of the time in order to facilitate understanding what's happening, debugging, and so on. So let's start with basic constants in TensorFlow and how we can do a simple operation by summing two values. So here we can import TensorFlow. Typically we import it with this alias TF, and now we are going to create a constant of value 3, and we can even give it a name. This is useful when we draw the graph of the computation. We're going to see that next week when I show you how to use TensorBoard for these kind of things. We're going to create another constant here. We can specify the type of the values. Typically we're going to use 32-bit floating points because this is optimal for using with GPUs. So in this course, if you just want to install TensorFlow for CPU, it's okay. We're not going to do anything very demanding. But if you want later on to do something a bit more demanding computationally, then it's best to use the GPU accelerated version, and in that case it's useful to always use 32-bit floats because that's what is the native format in general in GPUs. So here we can now define these two constants and then apply the sum operator to the two constants and compute the total. So this is the basic idea of how we're going to build the computations in TensorFlow, and this allows TensorFlow to keep track of all the gradients that it needs when we want to train our networks. So let's see how we can complicate things a bit more. So in this case, if you're using the recent version of TensorFlow, the default mode is eager execution. So when you run this code, you get the result. So here in total, you already have the result value. If you want just to create the computation graph like it happened with TensorFlow 1, or if you want to optimize the computation, then we can have TensorFlow just create the objects required for these computations and then execute when we tell it to execute. We're going to see some examples of that next week, but for now we're going to work just with eager execution. So we can now increase the complexity of our model, add more constants here, multiply, and so on. This is the very basic process of building these computation graphs. But note that at this stage we're only dealing with constants, and this is not very interesting because we need something that we can actually change the parameters for training our networks. So what we can do here, we're going to see, is to create different kinds of objects, variables, for example. And these objects, the constant, the variables, all these operations in TensorFlow have this special format, the tensors in TensorFlow. So when you get the result, you get this a TF tensor with some kinds of values. But we can easily convert this, extract the values that we want for using, for example, with other operations, with NumPy, for writing the results or something like that, if we use the NumPy method of the tensor. So the NumPy method of the tensor will return a corresponding NumPy array with the data that we have in the tensor. Note that in these simple cases, these tensors are just scalar, they are just single numbers, but the tensor can be an n-dimensional array of numbers. So in that case, NumPy would return, the NumPy method would return the n-dimensional array that we have stored there. Okay, so let's implement logistic regression. This is the basic idea. We have this function that approximates the probability of some vector x belonging to class 1. The function has this form, is the sigmoid function here, and what we do is we have this set of adjustable weights that we multiply by the features of the point we want to classify. Then we have this additional bias weight. We apply the sigmoid function here, and this would be the output of our classifier that tells us the probability of belonging to class 1. So we're going to optimize the weights by minimizing the logistic loss, which has this expression here. And this is what we try to do in logistic regression. And we're going to do that implementing it as a neural network, a very small one, which only has one neuron with this kind of activation and this loss function, and use stochastic gradient descent to find the best values of our parameters. So this would be the computation graph, which also includes gradients for all these computations. Just to take a look at some parts, we have here this part where we have the x. The x is the input vector that we're going to multiply here by our weights. So this would be this operation. We have the weights here and the x. Our weights are initialized at random in the beginning. And we have some connections here in the computation graph for the gradients. And then we also have this bias additional variable that gets summed with the result here of the multiplication. And then we feed this into this function, which is actually the sigmoid function. The TensorFlow has this sigmoid operation, so it knows how to compute the sigmoid. It also has the gradients for the sigmoid. And then we move on to the logistic loss, because now we're going to connect this during training to this computation with the logarithms and these subtractions and so forth. So basically, when we define this as operations over tensors, TensorFlow will keep track of all these operations so that it knows where to apply the specific gradients and how things fit together in order to use backpropagation to adjust the weights. So we have all these auxiliary graphs for the gradient descent optimization. We have the optimizer here, and now I'm going to show you how we actually specify these computations. So we have this data file. The third column is the classification for our data. So this is the data set that we want to separate with logistic regression, and we're going to read it and standardize the two features. So these are x1 and x2, for example. We're going to separate this from the columns of the labels, and we're going to compute the mean and the standard deviation and standardize this. So this part is what you already used to do, what we did lots of times in machine learning. We read the data, we subtract the mean so that it's centered at 0, and we divide the standard deviation so that the standard deviation of the data that we're actually going to use is always 1 in each dimension, and everything has the same scale and it's centered at 0. So now we're going to create our network, our very simple neuron to do logistic regressions. We have a set of weights. These are variables, and we have 2 of them. So we're going to create a matrix with 2 rows and 1 column in order to simplify the computation of the activations for a batch of examples. Remember, we saw this last lecture that we can use matrix multiplication in order to automatically compute that sum of the products of the weights and the corresponding inputs. And we have an additional variable, which is just a single scalar that we start at 0, which is that bias that we can add. So this will be this part here in our expression, where we're going to use matrix multiplication to do this operation over a batch of examples, and then we add the bias there. One important thing to note is that while the bias we can start at 0, it's not important, we need to randomize the initial values for the weights. Otherwise, if we have the same weight on both, then we always have the same derivative there, and our neuron will get stuck always having the same weight. Well, in this case, it's not very critical because we can have different input values that can change that. But if we had several neurons, we would risk having neurons that would be exactly the same and always respond the same way to the same inputs, and that would ruin our network. So even though for this case of 1 neuron is not very critical, in general, we need to start the weights at random values. Otherwise, we get our network with the cloned neurons and things won't work very well. Now we need to write a function for the prediction of the network. So this is what we have here when we receive an input and we output the probability of belonging to class 1. So what we do is we receive an X value that can be a matrix of examples in a NumPy array, a NumPy 2-dimensional array. So we're going to convert that to a tensor. We're going to create the tensor of X that is a constant tensor using the values of X but converted to a 32-bit floating point number. This means they are all in the same format and we can use GPU easily and so on. And now we're going to create a set of operations where we multiply the tensor with the batch of examples and the tensor with the weights of our neuron. So this is the multiplication. And then we add the bias here. And we can even create a name for the operation so that when we look at the graph here, we see the name there. This net result here is the result of these operations, the multiplication of the weights and the inputs, and then the sum of the bias. So you can add names to these different operations. The operations will be the nodes of the computation graph, and then you can see the names of the nodes when you print out the graph. I'm not going to show today how to see the graph. We're going to see that next week with TensorBoard, but this is how you can do it in order to make it easy to look at the computation and debug things, for example. And then we're going to create this output by applying the sigmoid. Again, you can see it here in the computation graph. It's called output there, and this is just the application of the sigmoid function, this function here, to the result of these operations. So this is the prediction. It's a tensor with the sigmoid activation of all the products of the vectors we input here as examples, and the weights that we have plus the bias. So this would give us a tensor that has the predictions for all the examples we input here in this function. And now we're going to create the logistic loss. So the logistic loss function will be this one. And we have, for this, we need the predicted classes that our neuron is outputting. And this we can assume to be a tensor, because we can assume that it will be supplied by this function here. And we also have the desired class labels, the target labels, which are the actual labels in our data. So in this case, we're going to assume that these labels may come as a NumPy array, because we read them initially here as a NumPy array. And now we're going to convert them into a tensor, the same way we did before. And we're going to create here the cost function or the loss function by computing the average, the mean. So this is called the reduce mean function here in TensorFlow of these products. You see we have the class label and the logarithm of the prediction plus 1 minus class label multiplied by 1 minus the logarithm of the prediction. So this is what we have here, the class label multiplied by the logarithm of the prediction plus 1 minus the class label multiplied by the logarithm of 1 minus the prediction. And our loss function will be the negative of this, just as we have here. And it's the negative of the average of this over a mini batch of examples. So that is why we are using reduce mean for this tensor, because this will be applied to all the examples we have here in the target labels and all the corresponding predictions. These will be tensors with the corresponding values for the complete mini batch that we are presenting. So now the cost will be a scalar vector, a scalar value, sorry. It's the mean for all of those, this value here. But we are setting up all these operations using TensorFlow operations and tensors, which means that TensorFlow can keep track of all the gradients associated with this. And that's what we're going to use now for training. We're going to create this function that gives us the values of the variables and the gradients. And we're going to get the gradients by using this gradient tape object in TensorFlow. What we do this is that we create a context for this tape object using this construct with creating a new object of this class that we call tape. And inside this context, we're going to run all the computations. So we're going to first pass our examples through our neuron by calling the prediction function. For a batch of X examples, it's going to pass through the neuron and activate the neuron. And then we're going to compute the loss using those predictions and the target labels. So this means that we are running the whole computation graph, and we are doing that in the context of this gradient tape that is keeping track of all the gradients associated with all these operations. So now we can call from this object the gradients, and we can specify that we want a gradient for this particular value, so at the end of all these computations, with respect to these variables, the weights and the bias, because these are the variables we want to adjust. And so this will give us the gradients for these tensors of variables. And we also can return, this is just for convenience, because note that these weights and bias are global variables here, so we could access them outside anyway, but we can return this just for convenience because of what we do here during training. So now for training, we're going to create an optimizer. This is in this case, is the stochastic gradient descent with this learning rate. And this is the object that is going to apply the information provided by the gradients in order to update the weights. So stochastic gradient descent simply takes the estimated gradient, multiplies by the learning rate, and uses that to update the weights. But we could do that, or the parameters in general, it includes the bias. But we could use more sophisticated optimizers, for example, with momentum and things like that. So now we're going to create a batch size of 1. That is, we're going to present only one example at a time. We could do this with different batch sizes. The number of batches per epoch is just the number of examples that we have and an integer division by the batch size. And the number of epochs that we're going to do, that is the number of complete passes through all the data, is going to be 20. You can then play a bit with these values, so the batch size, the number of epochs if you want. But now the actual training of our neuron will be like this. For each epoch, we're going to shuffle the examples, that is, get a set of indexes that are in random order. And then for each batch, we will fetch the examples that we want from the shuffled order that we have. So we start the batch at one value, go take a slice of the size of the batch size, starting at this point. And so basically we are reordering our data and taking out batches of whatever size we specify here. In this case it's 1, but we could use, for example, 10 or something like that, and it would take a slice of our data in this random order. Note that randomizing the order is done for each epoch, so that then we take different sets of examples along our data set. We are not repeating examples. We could also do this completely at random. That would be another approach, but in this case we are always presenting each example once per epoch and covering all the examples per epoch. And now what we do is we call this grad function for the batch of examples and the corresponding target labels. What the grad function will do is create this gradient tape and do the complete computation, activate our network, and then compute the loss function. And this gradient tape will keep track of all the derivatives in all those computations and return the estimate of the derivative of the error function, of the loss function, with respect to each of the weights and the bias, so all the variables we want to adjust. And so we get here the gradients and the variables, and now we call the optimizer to apply all these gradients to all these variables. Now here it's a bit tricky, because what the optimizer wants to receive in apply gradient is a list of tuples where each gradient is associated with each variable, so that it knows which gradient to apply to each variable. But we can easily do that by zipping together the gradients and the variables, and we receive both in the same order from the grad function, because we call the gradient of the tape to give us the gradients of the weights and the bias, and we also return the weights and the bias in the same order. That's why I did this here, so that it would be easier to do this here without making mistakes with the order of the variables. So this is what we're going to do for each batch. For each batch, we're going to run the computation, keeping track of the gradients, and then using the optimizer to apply the gradients to the variables and update our parameters, which are these variables, the parameters of the neuron. And now we're going to just check what is the loss here. We're going to do a prediction for all our data and get the logistic loss for all our data. So basically what we are doing here is computing the loss on the training set and keeping track of how training is going. Note that we are not taking care of generalization, of validating this outside the training set and so on. We're going to start doing that when we use more complex models in Keras, but the purpose of this is just so that you understand in detail how things are working at the level of TensorFlow. Okay, so this is what happens when we are training. During these epochs, these are the number of epochs, we are changing the values of our parameters and adjusting the discriminant, lowering the loss function. So this would be the result after training of our logistic regression. Now we can do this to solve a different kind of problem where we don't load the data, but we use the OR function. So you can see here we have pairs of values, 0, 0, 0 and 1, 1 and 0. So 0 is false, 1 is true. And since this is the OR function, false or false will be false, false or true will be true, and the other will be true too. So this is the output, 0, 1, 1, 1. This is the desired output for these examples. And this will be the training set that we're going to use. So we're going to do this again. We're going to create a neuron with these two weights and a bias value. The prediction is the same here, but now we're going to use the quadratic error, the mean quadratic error between the output of the network. The output of the network is again a sigmoid. It can vary between 0 and 1, but the loss function will be the quadratic error. So you can use the square function from TensorFlow on the difference between the target and the prediction. We receive here the prediction tensor, and this would be a NumPy array with the target labels. We do the same trick as before, convert this into a tensor and then apply these operations. And the operations are squaring the difference between them and then computing the average of this. So the mean square difference between prediction and labels is our cost function, the one that we're trying to minimize. So now we just do the same thing. We create the gradient to keep track of the gradients and do the backpropagation. We create an optimizer. We determine the number of epochs that we want, the batch size and so on. In this case, we need a lot more epochs because we only have 4 examples. And so each epoch goes by very quickly. And once again, we do the loop for training, shuffling the data using the batches and so on. So this is the same recipe we used before. The only difference is that we are using the OR function. We are trying to learn the OR function, and we change the loss function to the mean quadratic error instead of the logistic loss function that we were using before. So this is the result. We need a lot more epochs this time because we only have 4 examples in each epoch, but our neuron learns to separate the false from the 3 true values, and it works. Okay, so now let's move on to the exclusive OR function. The difference is that for true or exclusive OR true, the result is now false instead of true. So this changes the problem very much, because now this point here will no longer be true, but it will be false too. And so it will not be possible to separate them with a linear classifier. So if we do this with one neuron, we get this kind of result. You can see that the error does not get below, the loss function does not get below 0.25, which is the square of 0.5. So on average, we are making half of our predictions are wrong, and that will result in this value for the loss function. Okay, so here you can see that our neuron cannot learn to separate these data, and so we need to go beyond this to a more complex network. So basically, one single neuron can work for linearly separable classes. You can try this, for example, by loading this data here, and it doesn't work if we don't have linearly separable classes. So you can also, you have these data sets on the zip file, you can experiment with them and see what the loss function looks like, the error here. So we're going to create a multi-layer perceptron, and this will be the exercise part. What I recommend is that you follow this tutorial to really understand the details and also to check if everything is working, because you should have TensorFlow by now, but sometimes you're going to find that some things are not working properly, and I can try to help with that. But after you do this part, you're going to add one hidden layer to solve the exclusive OR problem. And the way this works is that the hidden layer will change the representation of the data. And so what the output neuron is seeing is actually a transformed version of the data, where it can, with a linear discriminant, separate the two classes. Now, to do this, you're going to have to change those prediction functions, the prediction function, and the variables that you're going to use in order to add this additional hidden layer. And now, to generate the data, you'll just use the exclusive OR function here. So the table, the truth table for the exclusive OR. And when you train, you'll eventually see that the loss values should come down pretty close to 0. And this is because the hidden layers are changing, the neurons in the hidden layer are changing the representation of the data, and so the split that is done by the output neuron is equivalent to this kind of separation here. Okay, so to sum up this part, we covered the very basics of TensorFlow. This is just to show you how things work and so that you understand how TensorFlow is working. And this idea that TensorFlow will keep track of all the activations, the elementary operations that we use, and all the way to the loss function. It keeps track of all the values and the gradients, and then applies automatic differentiation to enable us to compute the gradient of the target function, the loss function, with respect to all the variables that we want to update. So we create those tensors as variable tensors, and then we use in this case, the gradient tape to keep track of all the gradients and feed that into the optimizer. This will not be how you're going to solve these problems further on, because this will be all encapsulated inside Keras, which is a lot more practical, because as you can see in these examples, we have quite a bit of code here for doing the actual training, for keeping track of the gradients and so on, which basically looks always the same. It's basically the same code repeated for each example, and this is not very, very practical. So once we encapsulate this in Keras, we no longer care about these details, and we can focus on working with more sophisticated architectures. But it's important to understand how things are working there, because sometimes you may need to fine-tune some details. So for today, in the tutorials, I want you to follow this lecture. You have the slides online. Look, you can copy the code, reproduce the code yourself, but then experiment a bit and follow the lecture all the way to the end of the one neuron examples, and then think about how to extend that to a network with more than one layer. So this will be the exercise. Think about how to solve the exclusive OR problem, and then you can complicate the network more and solve apply to the other data files that you have there. But basically, think about how you can add the additional layers and what parts of the code you need to change in order for that to work. So for now, I'm going to log into Zoom, and we can have the questions session. Okay? See you soon.